Hello. Okay, so thank you for the introduction. So good afternoon, everybody. My name is Quang-Trung, and today I will present our talk titled Automated Lemma Synthesis in Symbolic-Heap Separation Logics. And this is so I work with my colleagues, Dr. Chanh, my supervisors, Dr. Siau-Cheng Khoo, Dr. Wei-Ngan from National University of Singapore. So we are interested in the problem of automatically verifying software using separation logics. And in this approach, a verification system often verifies program in three main steps. First is to specify the program behaviors using separation logic formulas. And the second is to analyze the programs against its specification and to obtain the verification conditions. And finally, to prove the verification condition to decide whether the program is safe or not. And so why do we use separation logic? So for some of the audience, if you are not familiar, this logic can provide an expressive model of the content and the separation of data structure. For example, we consider the data structure self here. Its model is an element of the single linked list, which has to fill the value and the next field point to the next pointer. And the singleton heap predicates here, x pointer one new can model the element having the address x and point to an element of the linked list having the value 1 and the next field is new. And separation logics also have to model the separation of elements. So here we have formulas using the separating conjunction operator. And this formula saying that we have two elements pointed by y and by z, and they are allocated separately in the memory. And separation logics also model the shape of data structure by using inductive heap predicates. So we consider another data structure node here, which is an element of a doubly linked list. And we can model the segment of a linked list by using the two predicates, the normal segment or the reverse segments. So each predicate here has four pointers, point to the head of the segments, the tail of the segments, the previous node, and the next node. And in the base scale definition, so the segment can contain one node, or it can be expanded in the head in the normal doubly linked list segments. And in the reverse doubly linked list, the element can be expanded in the tail. And both the two predicate segments here has at least a length of 1. And what are the verification conditions? So they are the constraint generated when proving the precondition of a function call, or proving the post-condition of a function definitions, or when we perform normalization or transformation of program state. And they often appear in the form of separation logics entailments. So here are the two examples of the separation logics entailments. The first entailment saying that normal doubly linked list segment is also a reverse doubly linked list segment of the same length. And the second entailment saying that the combination of two normal doubly linked list segments is a doubly linked list segment of the total length. There are many approaches to prove separation logics entailments, and some of them predefine the syntax and the semantics of the predicates, or some of them translate the separation logic formula into formulas of other theories like the graph, automata, or set theories. But this approach normally restricts the expressiveness of the logics. And they also approach using cyclic proof or induction proofs. So in these techniques, they can apply the induction hypothesis to prevent the unlimited unfolding of inductive heap predicates. But this approach are normally incomplete due to the failure of cut elimination rules in inductive theories. So we consider the problem of proving the following entailment if we say that the combination of two linked list segments, one is modeled by the reverse doubly linked list of the length n, and the other modeled by the normal doubly linked list of length 200, can be split into two parts. The first part is a normal doubly linked list of length n plus 199, and followed by an element. So the approaches that predefine the predicates or translate the formula, they do not both support the arithmetic constraint like the length property here, or they do not support the reverse Bayesian predicate like the reverse doubly linked list. Now we consider an attempt to prove the entailment using structural induction. So we first record the entailment as an induction hypothesis. Here, the own variables are renamed to avoid confusions. And now we unfold the first predicate by its inductive definition to define the entailment E1 prime here. But then we cannot apply the induction hypothesis to prove E1 prime because when we perform the unification between the predicate of the same symbol, the variable Q here is mapped into U, while Q here is mapped into V. So Q is mapped into two different variables, U and V. So this is an invalid substitution. We can perform another preprocessing like folding this part of the entailment E1 prime to have a normal doubling list segment of length 201. But then we cannot apply the induction hypothesis here to prove the entailment E1 double prime because when unifying these two predicates, the constant 200 cannot be mapped into 201. So structure induction proof fails to prove the entailment E when unfolding the first entailment, and it also fails to prove the entailment E when unfolding the second entailment. And in general, all existing cyclic proof and induction proof fail to prove the entailment here due to the same reasons. But the entailment E here can be proved by using the auxiliary lemmas. So here we consider proof tree of the entailment. We see that we want some lemma to relate the reverse doubling list in the antecedent with the normal doubling list in the consequent. So we want some lemma like I want to convert the reverse linked list into a normal linked list, and we can apply the lemma in the antecedent to define new entailments. Now we want to find a new lemma that combines the two normal doubling lists and result in a lemma L2 that combines the two linked lists and return in the normal linked list of the length of the total length. We can apply this lemma to define a new entailment, and then we want to synthesize another lemma that split a normal linked list into a linked list and an element. And this is lemma like L3 when we want to split a doubling linked list of length at least 2 into a linked list of length n-1 and followed by an element. And we can apply the lemma here on the right hand side. And now we can perform the normal inference rules in separation logic to derive a pure entailment. And then we can invoke the SMT solver to prove the entailment here. So the question here is how to synthesize the auxiliary lemmas. In our approach, we synthesize the lemma in two main steps. First, we discover the lemma template, that is to synthesize the heap structure of the lemmas. And then we try to refine the templates by discover the Boolean constraint over the variable. And the constraint can be put in the antecedent or in the consequence of the lemmas. So we consider the first step to discover the lemma templates. We want to find some templates that having the similar heap structure with the entailments. So thus the lemma can be applied to prove that entailment. We can take a look at this example of the motivating entailment E here. So the possible lemma templates can be the lemma that converts one predicate symbol of the reverse doubling list into a normal doubling list. So we have the skeleton of the lemma here. So in this case, we arbitrarily name all variable differently. And note that the variables in the consequent are existentially quantified because initially we don't know the constraint about the variable. And we can also find another lemma template that's sharing the same heap predicate symbol with the entailments. And here's another template and another template. So in the second step, we will refine the simplest lemma templates first. So here are the two simplest lemma templates obtained from the previous slide. And what we want to do here is we want to synthesize Boolean constraints over all variables xi and ni in each template. So here xi represent the pointer variable and ni represent the integer variable in the templates. So where we can place the Boolean constraint, so we can place it in the antecedent of the templates, or we can place it in the consequent. And I will explain about these two steps in the next slides. And so in the first step, when we want to define the lemma template antecedent, our goal is to add more constraint in the antecedent to make the lemma valid. And what we do here, we represent the desired constraint by an unknown relation U here. So relation U will contain all variables of the lemma templates. And then we create an unknown entailment and then prove it by induction to collect the constraint set over the unknown relation. And then we solve the constraint set to discover the real definition of the unknown relation and therefore discover the lemma. So we present here the illustrating proof tree of the unknown entailment. So this entailment contains the unknown relation in the antecedent, and we apply the induction tree to derive new entailments. And then we have a step to apply the induction hypothesis to prove the entailment obtained from the inductive case unfolding. And then we can collect the constraint over the unknown relation, which are the constraint corresponding to the set A1, A2, A3 here. And we want to solve the constraint set A to find out what is the definition of the relation U here. And we do it by using template-based constraint solving techniques based on Farkas lemmas. So what we do here, we create a relation template with unknown coefficient to represent the unknown relation here. Here we separate the constraint over pointer variables and constraint over the integer variables. And then we will replace this relation template over the constraint set and apply Farkas lemma to eliminate universal quantification over all pointer variables and integer variables. Now we can apply SNT solver to find out what is the unknown coefficient of the pointer variable and the unknown coefficient of integer variable. And in our approach, we can solve the entire set here completely to discover a full solution, or we solve a subset to discover a partial solution. So in the latter case, we need to verify that the partial solution is a valid solution by perform the induction proof again. So we consider the example of when solving the constraint set here. When solving the full set A, we discover only a spurious solution. That is, the unknown relation here is equivalent to false. This is because of the second condition when we have that U implies false. So this is not a U full solution. So we will solve a subset. That is, the subset contains only the first constraint, and in this case, we can obtain the definition of U. And now we can discover a lemma. Because this lemma needs to be verified by the induction proof, but we can normalize and to obtain the motivating lemma L1 that convert a reverse double linked list into a normal double linked list. In the other step, we can refine the lemma templates in the consequent by adding more Boolean constraint in the consequent of the templates. But then adding the Boolean constraint in the consequent is not good enough because sometimes the antecedent may be too quick. If we look at this entailment, so the antecedent say that we have a linked list segment of length at least 1. But in the consequent, the length is at least 2 because we have the length at least 1 here followed by another element. So if we keep adding the more constraint in the consequent, the lemma cannot be valid. So we need to do one preprocessing step that is to add some initial constraint in the antecedent. And we do that by adding one unknown relations which contain only variables in the antecedent, and then prove it by induction, and then solve it to discover a solution saying that the linked list in the antecedent must have the length of at least 2. And here is the preprocessed lemma template. Now we perform the second phase to fine-tune the preprocessed lemma template by adding more constraint in the consequent. And this constraint will contain all variables of the template. And we do that by create an unknown relation in the consequent here, and then prove it by induction and obtain this result. And we can discover a lemma, and which can be normalized to the motivating lemma L3, which split a normal double linked list into 2 parts containing a normal double linked list and an element. So we develop a proof system which contains general inference rules reasoning about the structure of the entailment, like the entailment having inconsistency in the antecedent, the pure entailment, the equality, existence of quantifications, empty predicate in the entailment, or heap predicate, or also a case analysis rule, and more detail can be found out in our paper. We also have the rule to perform induction proof and the rule to apply the synthesized lemma to prove the entailment in the left-hand side or the right-hand side. And more importantly, we have the rule to collect relation, the constraint over the unknown relation. And this rule will collect the constraint in the pure formula which has unknown relation, or in the entailment which has spatial antecedent or spatial consequent. And we also have the rule to collect the constraint when apply an induction hypothesis which has the unknown relation to prove the other entailment. So here is a proof system when we have the step to synthesize the lemma, and when we are in the synthesis mode, we need to collect the constraint over the unknown relation here. And so we implement the framework in a prover called the Songbird LS. It's an extension of our existing prover Songbird with the lemma synthesis features. And here is a link to the project website. And we conduct the experiment with the literature benchmark from the separation logic competition in 2014. And the benchmark from our previous work, we also created a new benchmark with more challenging entailment. And the experiment is conducted in Ubuntu environment. So here is the experiment with a literature benchmark. We consider state-of-the-art prover, including the slide, slick, span, cyclics, our previous prover Songbird, and then this prover Songbird with the lemma synthesis features. And these two benchmarks are from the separation logic competition in 2014, and this is a benchmark from our previous work. We report the number of entailment proof in each category, and the number in red are the best prover. We also report the average time for proving each entailment and the statistic about the lemma synthesis. So we can see here the prover Songbird with lemma synthesis can prove most of the entailment in all categories, and overall it can prove 414 entailments over 418, and which is about 99.04%. And the average time to prove each entailment is about 0.5 seconds per entailment. So it's quite fast in comparison to other prover. So our framework synthesized in total 34 lemmas to prove entailment, but only 22 of them are used to prove. So the number of lemmas synthesized is quite low in compared to the number of entailments. So therefore, we decide to synthesize, to create a new benchmark with more challenging entailments. So here, the entailment is more complicated. It contains more spatial predicates and more pure constraints. And we perform it also contains the arithmetic constraint and like the length, the sortedness. And we conduct the experiment with the 3 best prover from the previous experiment, including cyclics, Songbird, and the Songbird with lemma synthesis. So we can see here, the Songbird prover with lemma synthesis can prove 294 entailments in over total 300, and it's about 98% of the benchmark. And there are 421 lemma synthesized with 318 are applied, so the effectiveness of the lemma synthesis is quite high. And we also categorize the synthesized lemma in 3 groups: the lemma that converts one predicate into the other, the lemma that split one predicate into multiple predicates, or the lemma that combine multiple predicates into one predicate. And we can see here that the conversions and the splitting lemma are the most synthesized and applied. So to conclude, we consider the problem of proving sophisticated separation logic entailment with inductive heap predicates and linear arithmetic. And we propose a framework to automatically synthesize lemma to assist in proving the entailments. And the lemma are synthesized by using templates, induction proof, and constraint solving. And we integrate the framework into the prover Songbird with lemma synthesis. And here's the link to the website. And in the future, we would like to support more expressive logic fragments like containing nonlinear arithmetic or containing second-order constraints like the set or the multi-set. And we also want to apply into practical program verification like integrating into the heap-slick verification system. So here are the references we use in the talk. And here is a takeaway message, and thank you for your attention.
All right, so we do have some online questions.
Yeah.
The first question is how do you discover the predicates like list DLL?
List the
DLL, the doubly linked list
Yes.
predicates.
So the predicates is we consider the separation logic entailment competition in 2014, and then in this competition there are multiple predicates. So we just learn from this predicate to compose a predicate with the length properties. Do I answer the correct questions?
So, anybody have other questions? Or so there's another online question.
Yeah.
Why not use the reduced product of separation logic and polyhedral abstract domains?
Can you repeat the questions?
Why not use the reduced product of separation logic and polyhedral abstract domains?
So the question asks about why not synthesize the pure constraint in a polyhedron domain.
With the polyhedral, abstract domain.
I think our domain is more general than the polyhedron domain because we allow the linear arithmetics in arbitrary form.
Okay.
Yeah.
We have time for more questions. Yeah, if anybody wants to ask. Okay. There's a third online questions.
Yeah.
How do you handle the frame rule?
How do we handle the frame rule?
Right.
Yeah. So the system here is only handle classical entailment, like the heap in the antecedent must match directly with the heap in the consequent. But we can extend the proof set procedure and we can extend the inference rules to allow the frame rules.
Okay.
Yeah. So
one last question.
Yes.
What about lemma L2 that didn't look like the left or right side of the original entailment? This is probably very specific to the place we show lemma L2. But
Yeah,
if you think this is too specific?
I can show the lemma L2 here.
Yeah.
So can you repeat the question?
What about lemma L2?
Yeah.
That didn't look like the left or right side of the original entailment.
I see. So the question is about asking how do we choose the lemma L2 here? So because we want some lemma that share the similar heap structure with the entailment, so the way we select the lemma L3 is by collecting L2 here. Okay, so initially, so can I answer the question again? So the lemma templates we discover here is for proving the original entailment, but the lemma L2 here is for proving this entailment. So in this entailment, we can select the two predicates of normal doubling list here and one combined to one here.
Okay.
Yeah.
All right. Let's thank speaker again.
Okay. Thank you.